Hi everyone. So this video is an introduction to noise injection. Now in the last video we discussed dataset augmentation, right? And that we mentioned that in some applications, like if your machine learning algorithm is processing received signals of received samples of a wireless signal, then it's natural to inject noise in the input as a form of dataset augmentation. In general, noise injection, whether it happens at the input, at the hidden layers, or the weights, or even the outputs, it can be thought of as a method of dataset augmentation. But because this is an interesting topic by itself and requires its own discussion, so we are dedicating 4 videos to discuss it. So basically, it's much easier to interpret if done at the input that this is a dataset augmentation. But you could also think of the other forms of noise injection as dataset augmentation at other levels of abstraction, as we mentioned in the last video. Now let's introduce in this video in particular what adding noise to weights mean. So let's say I have so this is the cost function, right? So the y-axis here is the cost, right? And let's say the x-axis is the w, right? And this is a simplification, assuming there is just one w, right? There is just one weight parameter, right? And let's say this is how the cost will look like. So there are 2 minima. Let's say these are leveled. They are the same, right? So there is 2 optima to this cost function, one at this w1 star, right? And the other is at this w2 star, right? So what adding noise to weights mean is that I would prefer w2 than w1, w2 star than w1 star. Why? Because when I add noise to w2 star, I'm still within a minimum cost region. If I add the same amount of noise to W2 star, then I get out of the optimal cost region, right? So that means, so basically when you add noise to the weights, you are perturbing the weights, right? So you are forcing the network, you do that while training, right? So you are forcing the network to do what? You are forcing the network to be robust to changes in the weight parameters that it selects in every training iteration, to small changes, right? And the larger the noise, you are forcing the network to look for a flatter and flatter region where the cost function is optimal. Right? So it adds a preference. So before regularization, before injecting noise to weights, W1 star and W2 star are the same, meaning that the network is indifferent whether it reaches W1 star or W2 star. But with adding noise to weights, maybe the training algorithm will not be satisfied with the solution at W1 star, because when it injects noise to W1 star, the value of the cost function goes up. But then it becomes satisfied when it reaches, so it keeps exploring and it becomes satisfied when it reaches W2 star because it's a flat region. It's a flatter region, right? So this is a high level interpretation, right? But another way of looking at adding noise to weights as part of the training of the machine learning algorithm is that you can think of this as a stochastic implementation of Bayesian inference over the weights. So what does it mean? Bayesian inference over the weights, meaning that I want to find the maximum likelihood. What's the most likely value of the weights given the training examples? What does a stochastic implementation mean? It means that instead of my objective being finding exact values for the weight parameters, no, my objective becomes finding regions or probability distributions of the weight parameters. And these probability distributions are represented by the value of the weight parameter that the training algorithm is choosing and the distribution of the noise around that value, right? So for example, if the noise is uniformly adding a certain amount to the weight parameter chosen, or subtracting a certain amount from the weight parameter chosen. Then what I am learning is a region of uniform values from the minimum value to the maximum value around the weight parameter value chosen by the training algorithm, right? So another interpretation of injecting noise to weights is that we are implementing, it's a stochastic implementation of Bayesian inference over the weights, where the weights are represented by a probability distribution that reflects the structure of my uncertainty about the final function, right? So it's really probabilistic learning when you do that. You're not learning an exact function, but you're learning a probabilistic function. The function is likely to be between this and that, right? So this is really interesting because we are really embracing the fact or admitting the fact that we don't know, that we will be unable to learn the exact function, but rather we are learning a probability distribution of the likelihood of the function that represents the training examples. Thank you.